Okay, so in this video I want to talk about Gaussian elimination. So Gaussian elimination is a method that we can use to solve a set of simultaneous equations using matrices. And I know that there is a method in the A-level further math syllabus where you form a matrix out of the variables of the coefficients of the variables in the sets of simultaneous equations, and then find the inverse of that, etc., etc. But Gaussian elimination is a different method and can actually be more effective. And that's because Gaussian elimination works well with bigger matrices. So, for example, with 4 by 4 or 5 by 5 or even 6 by 6 matrices, finding the inverse of those matrices becomes quite difficult. Whereas with Gaussian elimination, you don't have to find the inverse of the matrix. So it can become much easier to calculate the solutions this way. Also, Gaussian elimination works with any size matrices. So, for example, it would work with a 3 by 2 matrix, or even, for example, a 10 by 4 matrix. It doesn't matter. So I'm just going to give an example of how Gaussian elimination works. So let's say we have the three equations. X plus y plus z is equal to 3. 2x plus y plus z is equal to 4. And x minus y plus 2z is equal to 5. I'm going to label the equations 1, 2, and 3. So first, we're going to form a matrix. And this matrix will be similar to the one that you would make to carry out the method in the A-level further math syllabus, but it'll be slightly different, and you'll see how. So the first thing we do is we look at equation 1, and we get the coefficients of the variables. So x has a coefficient of 1, so we write a 1. Y has a coefficient of 1, so again we write 1, and z also has a coefficient of 1, so we'll write 1 here. If we then look at equation 2, the coefficient of x is 2, so we write a 2 here. The coefficient of y is 1, and the coefficient of z is 1. And then for the third equation, we have 1 minus 1, which is the coefficient of y, and then 2. However, we're going to draw a line here, and now we're going to add another column, and that column will just be the right-hand side of each of the equations, the ones with the side with the constants. So we'll have 3 here, because in the first equation we have x plus y plus z is equal to 3. On the second row we'll have 4, and in the third row we'll have 5. Now this matrix here is called the augmented matrix. Augmented matrix. So augmented matrix, and it'll be key to allowing us to carry out Gaussian elimination. Okay, so we are now going to perform Gaussian elimination on this augmented matrix. And by the way, if we have an equation ax equals b, where a is a matrix and b is a vector, the augmented matrix would be written as a b, just like this. So the first thing we're going to do is look for the leftmost column that is not all zeros. And this is clearly the first row here. Once we found that, we have to get a non-zero entry at the top of this column. And as you can see, we already have a non-zero element on top of this. At the top of this column, we have a 1. The next thing we have to do is make this top entry 1, which again, we already have. So the next thing we have to do is add suitable multiples of the top rows to the rows beneath it, so that all the entries below the leading 1 become a 0. And this here is the leading 1. So we want to make this 2 and this 1 0. And the way that we're going to do this is by using elementary row operations. So what are elementary row operations? What are elementary row operations? Elementary row operations consist of 3 different operations. The first one is you can multiply any row by a non-zero scalar. So for example, I could multiply all the elements in the top row by 4 or -1 or a half. The second operation is you can interchange any two rows. So I could, for example, swap row 1 with row 3. And then the last operation is that you can add multiples of one row to another row. So I could add 2 times row 1 to row 2, for example. Okay, so knowing that these are the different operations we can do, we need to make the second row start with a 0. And the way that we're going to do that is to take away 2 times row 1 from row 2. So if we write it like this, so row 2 minus 2 times row 1, that will give us, so we'll have 1, 1, 1, 3, and then 2 minus 1, well, that'll give us 0. 1 minus 2, that'll give us a -1. And then 1 minus 2 again will give us -1. And then 4 minus 6 will give us -2. And then the last row will be the same for now. If we now make the third row start with a 0, so the way we're going to do that is taking away row 1 from row 3. So row 3 minus row 1, and that will give us, so we'll have 1, 1, 1, 3, and then the second row will be the same, so 0, -1, -1, -2. Row 3, while 1 minus 1, 0, -1 minus 1, -2, and then 2 minus 1 will be 1, and then 5 minus 3 will be 2. So that's the first iteration of Gaussian elimination. So now we are going to ignore the first row and carry out the same operations again. So this time we again look for the leftmost column, but because we used the first column, we now use the second column. And like before, we make the entry at the top of this column non-zero. You can see that we have a -1 here. And remember that this is the top element of the column because we are ignoring the first row. So the next thing we have to do is we have to make this -1 a 1. And the way we're going to do that is we are going to multiply row 2 by -1. So minus row 2, and that'll give us, so 1, 1, 1, 0, 1, 1, and then row 3 will be the same as well. And then we'll have 3, 2, 2. Now we need to make the elements in that second column beneath that leading 1, which is here. This is the leading 1. We need to make those elements 0. So what that means is we need to make this -2 become a 0. And the way we're going to do that is add 2 times row 2 to row 3. So if I do row 3 plus 2 row 2, that'll give us 1, 1, 1, 0, 1, 1, and then we'll have 0, 0, and then 1 plus 2, 1 plus 2, that'll be 3, and then we'll have 3, 2, and then 2 plus 4, that'll be 6. Okay, so we're almost there. We now have to just do one more iteration because we now ignore the top 2 columns and just focus on the third row. So like before, we find the leftmost column that is not all zeros, but because we already used the first column and we used the second column, we now have to use the third column. We now get a non-zero entry at the top of this third column, but because we're ignoring the first 2 rows, the topmost element is 3, which is non-zero. Next, we have to make this entry a 1, and the way we're going to do that is by multiplying row 3 by a third. So a third multiplied by row 3, and that'll give us 1, 1, 1, 0, 1, 1, 0, 0, 1, and then 3, 2, 2. And then the fourth step would be to add suitable multiples of the top row to rows below that row, so that all entries below the leading one become a 0. But because we're on the third row, which is the last row of the matrix, we can't do that step, and so we're done. And this matrix that we have here is called the row echelon form. So I'll write this down. So this is row echelon form. So we can actually go one step further and put this matrix into something called reduced row echelon form. But before we do that, I'm just going to write the properties of a matrix in row echelon form. And I'm not going to bore you with me writing it out, so you'll come back to when I've written all the different properties. So as you can see, I have written the properties of a matrix in row echelon form. So the first property is that all non-zero rows begin with a leading 1. And just for clarification, a 0 row is a row where all the elements are zeros. And I'll just mark the leading ones just so you know what they are. So the leading one in the first row would be this one here, because it's the one furthest to the left in the column. In the second row, it would be this one. And in the third row, it would be this one here. The second rule is that a leading one in a lower row is further to the right. So as you can see, this matrix obeys that law. And then the third rule is that 0 rows are at the bottom of the matrix. So we have no 0 rows, so by default the rule is obeyed.